So this video will be the second part of Module 6, Lesson 6 on graph optimization. And in this video, we'll be working through the exercises. So on your screen, you'll see the first exercise, which says, given the following sets of points in the unit square, find the shortest circuit that visits all the points, and find the circuit that is obtained with the strip algorithm. So remember that the strip algorithm is used to solve the traveling salesman problem. And this first set here, set A, the way that we're going to interpret this 0.1k is as multiplication. So the points in this set are going to be 0, 0, 0, 0.1, 0.1, 0.2, 0.2, up to 1, 1. So these are all points in the unit square. I'm just going to draw them. They all fall along the diagonal line y equals x. Okay, so that's just a rough sketch, and let's say we're thinking about the unit square. So first of all, the strip algorithm says that we're going to divide the square up into strips. How many strips? Well, first we start with the number of points, in this case 11, and it says we divide 11 by 2 and then take the square root. So 11 divided by 2 is 5.5. 5.5 is between 4 and 9. So the square root, the square root of 5.5 should be between the square root of 4 and the square root of 9. In other words, this is between 2 and 3. So 2 is less than this square root is less than 3. And the strip algorithm says to take the ceiling of this number. So the ceiling function looks like this. And it just means we're always going to round up. No matter how close we are to 2, we're going to round up to 3. So this is going to be 3. So first, I'll divide my unit square into 3 equal strips. So each strip will have width 1 divided by 3. So I'm calling the width of the strip D. And then the first phase of the strip algorithm tells me to start at the bottom left corner, and I'm trying to find a circuit that passes through all of the points of minimum length. Well, I can see that if I start in the bottom left corner at 0, 0, and I need to pass through all of the points and complete a circuit, which means I need to come back to 0, 0, then the shortest path is going to be to just go up the diagonal and then back down the diagonal. So essentially I'm counting twice the length of the diagonal. Well, this is the unit square, so we know that each side has length 1, and using the Pythagorean theorem, I know that the length of the diagonal is the square root of 2. So the shortest path for part A is going to be twice the square root of 2. So now let's see what the path that I find using the strip algorithm would be. So the strip algorithm says to start in the bottom corner and go up. So passing through all of the dots in the first strip, I make my way up. Then in the second strip, I need to start at the highest most point and come down. So I'm going to draw this like this, as if I'm going around and back down. Now in actuality, this path would be the straight line path. I would just connect these dots using the straight line path. The only reason that I drew this path like this going around is to clearly indicate that I'm covering the distance by going up and back down. If I just went up and back down, it would be hard to tell because the line would be on top of each other. So I've drawn it this way, but we understand that this is actually, I'm traveling the straight line distance up and then back down. Then in strip 3, according to the strip algorithm, I'm again going to start at the lowest most point and make my way up. Then the last step would be to connect this back to the bottom corner. Again, I've drawn these as curved lines so that it's clear that in step 1 I'm going here, then in step 2 here, then back down, then back up, and back down. But when I count this distance, I'm going to count it as if I was just traveling along the straight path. So how am I going to compute this distance? Well, for each of these lengths, I'm going to just use right triangles and the Pythagorean theorem to calculate the distance. So the first stretch is from the point 0, 0 up to the point 0.3, 0.3. That's the rightmost point in the left strip. And so the distance from 0, 0 to 0.3, 0.3 using the distance formula or the Pythagorean theorem is going to be the square root of 0.3 squared plus 0.3 squared. That's equal to the square root of 0.09 plus 0.09, which is the square root of 0.18. And I'm going to do the same way of computing the distance for each of these. Remember, I'm thinking of them as straight line paths. So I'll skip that work here, but you can verify along with me if you wish to pause the video and count, that the phase 1 distance using the strip algorithm, well, first I'm going to go up in the first strip. The distance is square root of 0.18. Then, moving from the first strip to the second strip, I have to go from the highest point in the first strip to the highest point in the second strip, and that distance is also square root of 0.18. Then I have to go back down from the top of the second strip to the bottommost dot in the second strip. That distance is square root of 0.08. Then from the bottommost point in the second strip to the bottommost point in the third strip, that distance is square root of 0.18. Then from the bottommost point in the right strip to the top corner, 1, 1, is also plus square root of 0.18. And then finally I come all the way back down to 0, 0, so plus the square root of 2. Now if I add that up, I find that the phase 1 distance is approximately 2.4 times the square root of 2. So it is actually longer distance using the strip algorithm. And the reason for that essentially is that all of these lie on a straight line. So the strip algorithm here is not particularly effective. But let's go ahead and examine phase 2 of the algorithm. So I'm going to again draw this diagram, the 11 points in the unit square. So here's my unit square. The bottom left point is the origin, 0, 0. The top right point is the point 1, 1. Now the second phase of the strip algorithm tells me that I'm going to shift the columns to the left by half of d. So half of d, d over 2, is 1 over 6. So that's going to be something like this. Now my first strip is just 1/6 wide. Then My second strip is still the width D, so it's still 1/3. So it is actually going to pass exactly through the point 0.5, 0.5. And then the next strip is also 1/3. So basically the two strips on the left and the rightmost are half as wide, and we still have two strips of width 1/3 in the middle. Okay, so again, we repeat the algorithm. It tells me in the leftmost strip, I go from the bottom to the top. Then, in the second strip, I go from the top to the bottom. That means I'm going to go again up and down. And let me remind you one more time that we would actually travel the straight line distance. I'm just drawing them curved so that you can remember the order in which we're going. So up and then down. Then in the third strip, I go from the bottom to the top. Now in the fourth strip, I again go up and then down. So I go out to the corner and then down. And then finally, I need to close the circuit, so I need to go back to the point 0, 0. So I will draw this path. But keep in mind that I would, in fact, just travel in a straight line for all of these paths. But now my path is broken into 1, 2, 3, 4, 5, 6, 7, 8 little pieces. And I'll compute the distance the same way. So this first little part of my path is just to go from the point 0, 0 to the point 0.1, 0.1, 0.1, comma 0.1. So I would use the Pythagorean theorem again. And what I would find is that this first distance in the corner is 0.02 in length. So my phase 2 distances. First I go square root of 0.02. Then the next path has length square root of 0.32. Then the next path has length square root of 0.18. So now we've gone up, up, and back down. Then going up to the next one is the distance square root of 0.032, not 032, just 32. So 0.32. So now I'm here in the third strip. So then going up to the top of the third strip is plus square root of 0.08. And then going from the third strip up to the top corner is another square root of 0.08. Coming back down is square root of 0.02. And actually, from there, we come all the way back down. So I'm just going to write square root of 2. So if I add these all up, I would find that in phase 2 of the strip algorithm, the distance required is 2.6 times the square root of 2. So you can actually see that it's going up as I chop it into more pieces. And again, this is because these all lie on a straight line, so this is not perhaps the best algorithm to use for a situation like this. And all of these individual distances, all of these small square roots, I just found using the Pythagorean theorem, so you could pause here and verify these on your own. So that is exercise 1, or part A of exercise 1. We also will look at part A exercise 1 part B, where you have this set, 0.1, 0.3, 0.3, 0.8, and so on. These are all points in the unit square. So if I had to plot them roughly, say Here's my unit square. So I'll have maybe a point like here, 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 and here. This is just a rough sketch of the points, and there were 5 points. So I'll start in the same way. I'll say, in this case, n is equal to 5. This is part B. And so I take square root of 5 over 2, and the ceiling function of that is going to give me 2. So I'm going to cut my unit square into 2 strips of width 1/2. Okay, so my strip is of width 1/2. Then the algorithm tells me I'm going to start from the bottom left corner and make my way up. But I have 2 points that are actually at exactly the same height. They both have height 0.3, I believe, if we look. So that's this point and this point, that both fall in the first strip. If I had drawn this a little bit more accurately, this would fall exactly on this line, but when it falls on the line, we consider it to be in the leftmost strip. Okay, so according to the algorithm, I'm going to first connect these 2 dots and then go up. So in the leftmost strip, I'm always going up. Then I move to the top point in the next strip. So that would be here. And in the second strip, I go down. So I go down to here. And finally, I need to complete the circuit. So it looks like that. So this is the phase 1 of the strip algorithm. And as we did in part A, we would use the Pythagorean theorem, or the distance formula, to find each of these distances. Now, this first connection that I made, it's just a straight line, so we know that its length is 0.4. But with these other ones, I could use right triangles to find these distances. So I'm going to skip that work because I know that you guys can do college algebra, but I'm just going to write these distances for you. This would be square root of 0.29, square root of 0.17, square root of 0.68, and this is also square root of 0.68. So if we add them up, phase 1 0.4 plus square root of 0.29 plus square root of 0.17 plus 2 times the square root of 0.68 is almost exactly 3. It's 3.000 something. Okay. Now in this case, in phase 2 of the strip algorithm, your estimate will actually improve. So your estimate, or your the distance traveled, will become lower than 3. I'm going to leave this for you to try on your own. So remember what you'll do. You'll have your points here. Something like this. And you'll shift this guy by, so half the distance, so 0.25. It's going to look like this eventually. And then you still have half here. So that should be your setup. So imagine that these are your strips, and we know that in the leftmost strip we go from bottom to top. In the next strip we go from top to bottom. In the third strip we go from bottom to top, and then we close the circuit. So try this on your own, calculate the distances, and just a hint, you should find that you actually get a better distance, so smaller number than 3, when you do the strip algorithm phase 2.